Hi, thank you for being here. So I don't know what type of public you are. I come from the industry, so please, if you expect something more academical, I also come from academia, but long ago. You'll see a little bit of my background with my talk. So it will be a little bit of a hybrid between both of them. So don't expect it to be super academic or super industry. So I am originally a physicist. I am from Mexico City, so it is not a tech hub. It is not a science hub. So you usually do what you can do. So I was originally a physicist, but I started coding, and I found out that I was really good at it, and I was much more better at it than I was a physicist. So I transitioned. So, but I have always liked math, like a lot. So this is very important because my approach to computers and to physics has always been based on that. So now that I am in the industry and I work with the shiny stuff, and that might be boring for a lot of you because it sometimes is for me, with Go and Kubernetes and containers and Docker, all the trendy stuff, that I work in Silicon Valley, so you can imagine what type of things. However, my personal preference is the Beam programming, and programming in Beam with Erlang, with Elixir, and stuff like that. I'm not saying that I hate what I do, but I am not. But at some point, like all the background that I've had, like in the academia, and also with all the Beam conferences and all the Beam people that I know, have allowed me to propose new visions and new perspectives in my bubble community. Sometimes I am listened to, sometimes I am not, but well, and thank you for being here. So a lot of my background depends on the work that I have done, which is very specific. So before moving to Silicon Valley, I used to work with very large distributed, highly concurrent systems in Latin America, which are like a different beast of its own kind. Not necessarily more complex or more simple. They're just different in the way that we have to deal with a lot of constraints. Since we're not a tech hub or like a region or an area that is famous for their technological points of view, you usually don't work for technical people. Like, you're usually the technical people, and you have to convince like your bosses or your managers to give you money for the most basic resources. They don't care if it's a distributed system or how complex it is. They just want it done. So, and they don't care if it's just a website or like the biggest telecommunication system you have had to deal with. So that is very interesting, like as opposed as my career right now, where you basically ask for anything and you get it, which I don't know. This kind of experiences made me very resourceful, and I am very thankful for that. So I'm always trying to optimize. Even if I don't need it anymore, I try to strive for that. And well, as a very personal subject, technology for me is a means of social progress, like economical, social, cultural, etc. for people who look like me. So it is like very important, a very important part of what I do, why I do what I do. Okay, so this talk will be divided into three. The first part into distributed systems, the second part graph theory, and the third part in topology. That is like the main part of the talk. Now, since this is a mixed audience, please keep in mind that the topology term that we'll be using right now is the math term. Not like, I have dealt with a lot of engineers that like to use the term in a very lax way. Like they do any diagram, like basically any diagram, and they call it topology because it sounds very fancy. But aside from personal preferences, right now for the purposes of this talk, we're going to talk about the math perspective of topology. And well, all these three concepts have in common connectivity, of course. Well, so let's dive into the first part, is distributed systems. Now, we shall start with a very famous and very overused quote about distributed systems, Leslie Lamport. But it will be useful as a foundation for the rest of the talk. So a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. So a lot of this happens because when we have a distributed system, no matter how big or how small, we usually are not aware of all the possible states of the world that can happen within our system. So usually when something fails is in production in terms of the industry, and when everything is on fire, when the customer is super angry and you don't know what to do. So an ideal distributed system would be fault-tolerant, highly available, recoverable, consistent, scalable, and with predictable and super great performance, and secure, none of which is offered by Go, for example. So building very popular and very famous, Kubernetes, for example, that is mainly built in Go, but is really Bash. With this in mind, it's sort of impossible. Well, not impossible, because nothing is impossible in these areas, but you know what I mean. So I have learned to navigate around it. A lot of these problems can be really solved thanks to Erlang, but no one listens to me. So no, but really something that I have learned. So this is an anecdote that it was not originally included in my talk, but you will appreciate it. So I think it was Elixir Conf last year. I gave a talk on my transition from Go to Elixir and back and forth. And I was asking friends on Twitter, how do you deal with fault tolerance in Go? And people were like, oh, it depends. You would like to make a more specific question, I don't know, or with tears or with alcohol or stuff like that. But then if I asked my Erlang or Elixir friends, how do you deal with fault tolerance? The answer was very direct. It was with processes, and that's it. So even though it was funny, it's real and painful. So, but one of my friends that used to work for the Go programming language core team came up with the most mature and serious answer, and it was you design for failure. Since, for example, in Go, I will talk a lot about Go and the bad parts of Go because that's my experience, but feel free to make the analogy to any tool that you use. In Go, things panic. We have a very useful and very strong standard library, but the moment you decide to use a third-party library that, for whatever reason, is not consistent, doesn't work, or fails, your whole system can go down. Not even that part of the system, but the whole system, even the one that was built with the strong libraries from the standard library. So you have to design your programs, your systems, your distributed systems with failure in mind. So something that I took from physics is if the probability of something happening is 1 in that number, how often will it really happen? So in real life, you would say never. But that number in physics is all the time. If it happens one time, at the quantum level, it is sure that it will happen all the time. So translate that in my world of the industry, about servers or the infrastructure of an outage, or if a service is not available, a service that gives you money is not available even for 5 seconds, 1 second, or the right second where the most important customer was looking. So it doesn't matter how high the probability is or how low, it exists. So at scale, this goes evidently higher in terms of downtime. So now we have the verification of a distributed system. That is why you came here, I guess. So we have, before diving into the real what I can offer to you, like my new perspective on the verification of a distributed system, I want to reflect a little bit on the problems and the current state of verification of distributed systems. So, yeah, here. The first is that the first problem that we have is that we have to have control and visibility over all the interconnections of our systems, which is very hard. A lot of people say it's impossible. So what do we do in the industry? Like, I wrote solutions there, but they're not solutions. They're like alternatives. There's like monitoring, either like with Prometheus, New Relic, Datadog, or whatever you use. Nowadays, chaos engineering, thanks to what Netflix decided to propose years ago with Chaos Monkey and all that. On-call rotations, testing in production, whether it be on purpose or not on purpose. But, well, those are the alternatives. I have been in on-call rotation when one of our clusters died because of an electrical outage. So there was nothing I could do. I couldn't like go and fix it. So it's painful. So if we could have had anticipated that case before it happened and not being able to recover it as soon as like with a command line thing or whatever, it would have been very useful. And then we have those systems that are actually formally verified, like Amazon Web Services and very big companies that can actually afford this. Because first of all, it is very painful. It takes a lot of time and it takes a lot of money, which is like twice the money because it's the money that you spend, and since it takes a lot of time, time is money, you know? So I don't have to tell you how to verify or how a distributed system is verified, but let's just dive into the very basic concepts. So we can use like formal specification languages or model checkers, etc. But as I said, all of this takes time or money, and of course expertise. And like you have to know the right company that does this, and nobody has time for this in the industry. And still, like even if you decide to do it, it still requires the definition of the program or the system or the state of the world of all your interconnections, possible failures, and correctness definitions. So even if you decide to do it, if you have all the resources, you still have to do like this, like the first part, what everybody in the industry says it's impossible, like to have all the states in mind, to know all the interconnections at the same time, you still have to do it. So it's like sort of a cyclic problem, and no one does it. Because I think that nobody does it anyway, because none of those systems will ever pass. But, but yeah. Okay, but what if I told you that we do have a tool in the world that allows us to see all the interconnections and all the possibilities at once? Well, at once. Well, it is not graph theory, but let's start with graph theory. I'm not going to explain to you what graph theory is, but like it's like the first topic to dive into the most important part of this talk. So, oh, by the way, the work presented here is part of my postgraduate studies that I did back when I was in academia, and I'm not in academia anymore, but I am now working with distributed systems that actually make money. So it's like a healthy balance of both. So I'm trying to implement these concepts with people that don't listen to me, but I'm trying really hard to make them listen to me. No, like I'm not complaining. It's like it's hard, you know, like the transition between both. It's like academia sometimes like has a lot of papers that are not possible to implement, and not because of the impossibility of the math or the computations, but because of money or whatever. And then the industry comes up with a lot of new solutions that is like, hey dude, there's a paper that was there like 20 years ago. So there are a lot of stuff like that. No, but seriously, in all seriousness, I would love to make an impact, like a broader impact into the distributed systems in the industry world, based on all the things, all the knowledge that is already out there. And this is not entirely my work. This was like my PI's work and a lot of colleagues' work. But my theory, my personal theory, I will present it at the end of this. But well, let's go back into graph theory. So it's a mathematical structure used to model pairwise relationships between objects. The first recognized paper about this is the 7 bridges of Königsberg. Then K-connectedness is how many nodes we need to disconnect a graph, or the otherwise, like for it to stay connected, and verify points of failure. So I dove into this a little bit because, okay, so if we describe a distributed system only with graphs, like with graph theory, we can have like descriptions like this that are still manageable. But what if our distributed systems, like the ones I have worked with, that I have seen either intentionally or unintentionally messy and big, look like this? So it is not impossible to operate with this, but it becomes even more complex than the original problem. So you don't want to deal with like a messier problem than your system itself. So, because like, for example, if you describe the adjacencies, I don't know how to pronounce this word in English, but that are really the interactions of all the components of your distributed system, it gets very difficult to manage. So for all those that are not very familiar in terms of the math concepts, like any of these interactions can be user with a computer, a user with a server with another server, a server with a cluster. Any sort of connections work in these definitions. Okay? So now, the topology, which is the study of geometric properties and spatial relations unaffected by the continuous change of shape or size of the figures. So keep this in mind because it is very, very important for the rest of this. So properties remain invariant under continuous stretching and or bending of the objects. Okay, so here I can see this, but okay, whatever. So there, it was meant to say different partitions or different divisions stay the same, even if we change them. So I mentioned that the first paper for graph theory was the 7 bridges of Königsberg because it is also one of the seminal works that is recognized as the first, even if not the first, like one of the first works published around topology. So a lot of these definitions come from like the pure math of being able to express anything, like don't even think in terms of systems, but just in mathematical bodies or entities, like something that can be expressed as a graph, and sometimes it gets messier as the interconnections grow or the number of nodes grow. You can express it as a topological object, and it is easier to manage and it's easier to see as long as you are familiar with topology, of course, but it's very easy. So for example, we have here figures and shapes that are exactly the same, topologically speaking, even if the visible shape is different, the interconnections are preserved. And the first example is very clear. It's just like stretched. In the second one, what we have is like basically the same interconnections, but subdivided into other parts, which make the study of the body and therefore the system. Remember that in this talk and in this world, we can interchange system with mathematical or topological body. So we can make subdivisions to make it easier to analyze. But I'll talk about this in a second. Okay, so we have defined topology itself and why is it useful if you were not familiar with it, or whatever. But there are like more subdivisions of topology, like different areas of topology, depending on your needs. So for this, we're going to use algebraic topology, which is like the most popular name of it right now. But for those of you that are more into discrete mathematics kind of thinking, maybe the name combinatorial topology makes more sense, but it's basically the same, and you can look for these terms interchangeably in the books, or on the internet, etc. So why combinatorial topology and not other type of topology? So because it studies spaces that can be constructed with discretized spaces. It allows to have all the perspectives, all of the system perspectives of a node available at the same time. With this, okay, I'm going to show you a diagram a little bit later. Then perspectives evolve with communication. And then a perspective is a view from a single node. Okay, so what do I mean with this? Okay, this is a very, very simple diagram. But let's say, I put here like a little table of interconnections or adjacencies. But this system is very simple, but it can scale with the same things in mind. So let's say that node 1 has perspective, from the perspective 1, it will have an interconnection with 2 and 3. There you go. Then perspective 2 will have an interconnection with 1 and 3. Etc. It's super easy. But think of this as like different states of the world, like a big, huge system. And when you have, I don't know, thousands of this, let this be Kubernetes clusters that work with 3 nodes are the minimum to begin working with. So let's say that we don't have 2 Kubernetes clusters, that we have like 1,000 Kubernetes clusters, and not that they don't exist independently, but that, I don't know, 50 of them coexist because they're replicas of something, or 10 of them are the database clusters. I don't know. So we can see all their interactions, like sort of with the adjacencies table, like in graph theory, but not only like judging the interconnections, but also like the sum of all the interconnections and treating them as topological bodies, which makes the study of them easier. Because once we have this, I don't know, here's a triangle, but we can maybe, in the case of Kubernetes, it doesn't make sense, but any other type of system that can be more complex. Not that Kubernetes is not complex, but Kubernetes is complex because it is very hard and the documentation is very deficient. But let's say that we have a more complex system and we can subdivide it. But I'll be back to this in a bit. I just wanted to show you that so that you could understand the term of what I meant with perspectives. Like, for example, let's say that we have this again, and for some reason, we didn't expect a connection to happen between 5 and 6, and then it fails in production, and then everything is down. So maybe we didn't see this because, I don't know, for whatever reason. The point is that we didn't see it on time. With this approach, with this perspective, if we are going to analyze each perspective at a time, there is no way we don't see this interconnection. Like, there is no way we can miss it. And that is sort of the point. Which, again, in this very simple example, it is very evident. But remember this at scale. Okay, so let's start on the principle that we have perspectives, okay? Then we continue with why combinatorial topology. the branches of topology in general differ in the way that they represent spaces and in the continuous transformations that preserve properties. Again, like all the topologies follow these rules, that it doesn't matter how much you stretch or modify the shape as long as the interconnections are preserved. But the difference is what are you focusing on? So, here. Space is made up of simple pieces for which essential properties can be characterized by counting, such as the sum of the degrees of the nodes in a graph. Again, like for example here. Here we have like a little bigger example of perspectives, of how can perspectives be perceived in a more complex thing. So here we have one, let's say this. So we judge the interconnections, and we can analyze this one, and then this one, and then this one, and all of them have this node in common, right? So we were talking about countable items, let's say. So the fact that we can count the adjacencies or the dependencies of this node makes it subject to be combinatorial. So we can add them, we can subtract them, we can duplicate them. It's all about the numbers. It's as simple as that. But that's what combinatorics do. So back again to this. Yeah. So then countable items allow combinations or interactions as much as you can. So that is why combinatorial topology is especially suitable for this. Now, diving into the theoretical part of this is like each view, each set of interactions has its own perspective of the system, and then we can add all the views, all the perspectives at once to describe a whole system. And for example, we were talking about the subdivisions. So not in every case, but in most cases, we can be able to subdivide, like let's say our first diagram of our system looks like this. But for some reason, like let's say this main, the front one, is about networking, right? So it really doesn't matter in this case if we subdivide it into smaller spaces, as long as the functions and the interconnections are preserved. Of course, like keep in mind that topology is a space on its own, right? So here, it deserves a whole talk on its own, like an introductory talk to topology. So it is not just like the diagrams and there you have the description. It's also what you can do with that. Like, for example, in graph theory, once we have like a table of adjacencies, we can know not only which node depends on which one, or how many nodes we need for the graph to stay connected and stuff like that. But we can treat them as graphs, and with the graph addition, graph subtraction, and all that. So once we treat our systems as topological objects, we can treat them under the laws of topology. So for subdivisions to happen, if you want to dive in on your personal free time, there are some rules that apply. Not only on the systems level, but on the mathematical level. And if you make that pairing, like that comparison, you can treat your broader distributed system as a topological object, and that is very powerful, because you don't have to rely anymore on just like, oh, I think that these connections might happen or might not happen, or rely solely on the post tools like monitoring or like graphs, or graphs not in this sense, but like graphs in terms of behavior and stuff like that. Okay, so we can subdivide this as long as they follow the topological mathematical rules that we're not going to discuss right now, which makes it easier for the study of our systems. Now, verifying a distributed system with combinatorial topology. Distributed systems can be formally verified by treating them as a set of topological entities. Okay, so this is where my personal thesis comes. So all of this before is like the aggregation of the work of a lot of people, including myself. And I mean, topology is not new. Distributed systems are not new. But like where they converge is like a new point of view, like mostly proposed by Sergio Raxbaum and Maurice Herlihy. And I was lucky enough to work for my postgraduate studies with Sergio. So that's where I was already working with distributed systems before at the academic level. But once I learned this perspective, it was like life-changing for me. Because as I said at the beginning, the reason why I came both to physics and computers was math. And that was like my main point of view. So once I could use math, not only like in general that people say that, oh, you should be good at math to be good at computers or not or whatever, but just like because it has the same type of method thinking or logical thinking. Not only because of that, but like for the very first time, I could see like the math skills that I had that could be literally and directly applied into something that worked or might not work, but it was a subject of study. So it is tremendously like helpful to have a perspective like this, and especially in an industry that struggles a lot with this type of problems. So going back to my experience there, besides what Go has, like bad or wrong or good or whatever, the systems and the type of work that we do is very iterative, very fast, very, I don't know, not the best approach for correctness in systems. So since we have a lot of customers, a lot of business requirements, even if I have worked in open source, and it is not the dream that people think, because you still have to be subject to business or to partner decisions, stuff like that. And I mean, it's fun, but you have to work around a lot of constraints that are not necessarily pro-correctness. So the industry values more performance than correctness or validations. So that's why we still have a lot of very important, very famous distributed systems or tools failing in very, very simple ways, if to say it like that. So something like this, we're not saying that it's a solution because there are no silver bullets, of course, but it's something that might help us, not only people, but us, like things that I am working on at this moment, to have a better set of tools and being able to focus on the problems of distributed systems. Because right now, the state of the world in the industry for distributed systems is more about tooling to prevent failure rather than solving problems of distributed systems. So it is very important to find like workarounds or alternative solutions for this. Okay, so back to this. So up to this point, as I told you, it is the aggregation of work by several people, including myself. But which is like in conclusion for that part, basically, we have distributed systems. It is very hard to describe them, especially as they grow and at scale and all that. So it is very difficult to describe all the interactions before putting them into production. And once you put them into production, there's almost always something that fails. And that failure can be catastrophic in the sense of a panic or being almost impossible to recover. And that in my world translates into a lot of loss of money or a lot of waste of time of people working in weekends, stuff like that. So there are some processes to verify these distributed systems formally, etc. But these processes are not followed. And they're not a rule in the industry because they're very hard or expensive, etc. So until this point, this is what we have, like a topology as a tool to describe distributed systems, the end, right? So my thesis, my personal thesis, after working with Sergio's and Maurice's work, is that we can not only use topology to better describe our systems, but that we can also use topology as a tool to verify distributed systems. So how does this happen? In my mind, distributed systems can be formally verified by treating them as topological entities or as a set of topological entities that are subject to valid in terms of mathematics and the type of subdivisions that I told you. Analysis of the persistence and consistency of their interconnections or interactions in math paths, and offering a comprehensive set of states of the world, or the aggregation of these states of the world in order to describe the general state of the world. So what I am proposing here is basically combinatorial topological studies to verify, to formally verify a distributed system. Because the way it works for me is that once these entities, these bodies, are verified into their own set of mathematical rules, not even thinking about if it's a valid transaction in computer science, but like if it's a valid interconnection in terms of topological rules, then we can go ahead and describe like that state of the world. Oh, sorry. Yeah, that state of the world, and then go ahead and I don't know, treat them, make them subject of seeing if what does it take for this body to stay connected. What are the implications of disconnecting it, and also play with that, because like now on the not only on the mathematical level, but on the useful level, to play with possibilities like, what if I disconnect this node? Let it be k-connected or not k-connected, but let's say that it is still k-connected. In theory, if it is still k-connected after a disconnection of that node, the system should work. But then try and play with that. And then what if without this node we're not k-connected anymore on the mathematical level? But what if there's some sort of possibility that even if we have a failure, it can be a failure that doesn't impact our customers or doesn't impact like on a significant level? And then you can make that sort of decisions, like whether something is overkill or not, because let's remember that 100% reliability or availability or any Kath theorem subject that you want to focus on, 100% is mostly in the industry overkill, and it's not worth it because the customers never realize that. So you can make that sort of decisions in an easier way. So my proposal is that, like to use topological objects from the combinatoric perspective to formally verify a distributed system that, in my perspective, even if it does require like certain level of expertise on the mathematical level, on the practical side of it, there are more people that are able either to learn or that already know these concepts than the possibility of verifying a distributed system with the current methods. You know, also, it is not, as I said, it is not a silver bullet. My proposal is not a silver bullet, but a lot of these verification processes don't work alone. Like the very best thing to do right now is to work with different methods at the same time to provide like a more reliable assessment. So this can be like the final assessment or like the cherry on top of the cake in this case, or like pair the solution with like the current industry's procedures, like canaries, even monitoring systems. But even with new perspectives like this, the current alternatives that we talked about at the beginning, like monitoring, chaos engineering, on-call rotations. In the end, for example, chaos engineering is like building tools to break things on purpose. So how do you know what things to break? You have to have states of the world. You have to know the most possible paths. So thanks to topology, we can describe things better. Also remember, like, if you're in academia, this is especially important, and it can resonate with you. When we have a research or a project, obviously the ultimate thing to happen, for us to happen, is to set a thesis and learn a lot from it and to verify it, and yay, we did it. But what happens in the middle is also very valuable, not only for academia, but like for the results, for things that can be useful. So here, even if my theory, my proposal of having combinatorial topology as a formal method of verification of distributed systems, or even if it is valid in the end, the steps in the middle are already valid, are very useful, and are things that are not being valued enough at this point in the industry. Like, let's say, again, chaos engineering. It's a very brilliant set of tools, like built and proposed by very brilliant engineers, but a lot of it is a lot of overkill, because again, you have to be aware of the most possible paths. So how do you do that? Like, basically just like sitting down and writing down all the possible paths that you can think of? Or, I don't know, there are many possibilities, but topology can really help with that, even if you don't use it as a formal verification system, or even if you are not interested in formally verifying your distributed system, but like as a tool, as a means of progress of the state of the world of distributed systems, I think is a very useful tool that I have started using in my personal academia industry work. Sorry, as a tool for myself and for my own knowledge, because I don't want the software that I write to break because of things that I didn't see, you know. So yeah, so that's basically what I propose. And if you have any questions, please let me know.
Questions?
Thank you. I'm very excited when people want to use maths to solve computing problems, and you want to use two different kinds of maths. Now, I have got a question as to how you envisage that in a little bit more detail. A distributed system consists of software that runs on different nodes. And what I have seen so far in your discussion is about the relation of the nodes, but it does not also reflect what software is run and how this software is affected by the connectivity of the nodes. Do you think that it can be extended, and how?
Yes, the proposal of not only the verification, but of the description of the system is that any entity, let it be the software itself or the hardware itself, decomposed into different components. Sorry for the lack of more vocabulary, but all of the entities that are part of a distributed system, whether it be the most simple one up to the most complex one, can be described as a topology entity. Now, maybe a single, let's say, a torus or a donut or whatever, doesn't make it for the whole system. Or it can be, again, like the same case of the graphs, that once you start describing a lot of objects, it becomes messier. But maybe you can have a set of topological bodies or entities in which you can describe a full system. But even if you have more than one, it's still, or n, it's still easier to describe them that way than with the traditional tools. Yeah.
Thank you for your talk. It's really interesting. You mentioned, I think, a person who works in that field.
Yeah.
And I was wondering if there are any resources or learning resources, academic or engineering.
So, well, they wrote a book that is based mostly on talks and papers that they had already scattered around the academia for many years. So the book is called Distributed Computing through Combinatorial Topology. Yeah. So it is a book. It is awesome. And although the first chapter is this, basically the basic concepts of this. The remainder of the chapters are more, how do you say that in English? It's like an overkill. It's like basically them, and I say this with love because I am the same way. They're basically showing off their math skill, which is great. But if you're looking for the computational part of it and the implications, it has a lot of, like, starting on chapter 2 or 3, it becomes really, really mathematical. And if you don't have a lot of I suppose you do, but for people that are not very familiar with distributed systems itself, like on the computer level, it can be a little bit difficult to map the concepts. But otherwise, it's a very good book. And you can always browse their names. Like one of them is Maurice Herlihy, with an H in both of them. And the person that I work with is Sergio Ragsbaum, like with a J in between. Okay. And this is basically their passion project. Both of them have been working a lot with distributed systems. And in case of Sergio, a lot of mathematical background and a lot of mathematical tools like this to describe a lot of entities in computer science that, since he's so good at it, it is better for him to study computer science that way, from that perspective, rather than overkilling processes of computers itself.
Do you have an example of a property that you want to validate on distributed systems?
Sorry? An example of a property that...
a property of a distributed system that you would want to validate with topology?
That I would validate? Oh, okay. So I think the question was if I have an example of a property of a distributed system that I can validate with this. So it all comes to interconnections. But let's say that what would happen, I have a cluster of whatever, let it be Kubernetes or not Kubernetes. And one of the nodes, we're trying to see what happens if that node doesn't fail but becomes idle or whatever. So we have to see, and for example, if this node, what will happen, what will the implications be? And this can be a server, okay? Don't think of it as a node or as a vertex or whatever. It's like a server. What would happen if this server goes down? And these are computers, these are users. So can we figure out new paths to recover this? If we can, how? Maybe this is part of a bigger topological space. So maybe on the other side of this, we have another server in which we can rely on. But maybe we don't. So that's exactly the point. Like if our system is designed like this, and the only, and let this be a server and these users, the only server that we have is this for some reason in our design. This is a very basic example, but it works like that at scale. If this fails, what are we going to do? So design a better type of system, a better type of diagram, a better type of shape, that sort of thing. And that happens in any case. Like let that be a server, a cluster, a computer, the hardware, any piece.
All right, thank you.
Thank you.